it okay with the microphone? Yeah, I guess.
Okay. Second talk of the morning section will be given by Alexander Shapiro from University of Notre Dame.
No, it's actually no longer.
Okay.
No longer
I
from
don't know.
University of Notre Dame.
People, we know a big news. And he will talk about quantum decorated character stacks.
Yes. Right. Thank you so much. It's a great pleasure, somewhat undeserved, to speak here. So I'll be speaking about some topic that also appeared in Anton's talk just an hour, well, 15 minutes ago. It will be moduli spaces of local systems. So let me say a few words about them. First of all, yeah, it's a joint work with David Jordan, Ian Lee, and Gus Schrader. This talk will be about attempting to relate two different ways to quantize this moduli space of local systems, because as we all know,
you need to stay here for the camera from that line.
Okay. All right.
From that line.
Okay. Well, as we all know, this character varieties or moduli spaces of local systems, they admit Poisson structure, and there are ways to quantize it. So we'll discuss that. All right. So the setup starts with an oriented surface S. For example, like this one, may have non-trivial genus, may have boundary, may have marked points on the boundary, a reductive group G. And then we consider these kind of log, underline, GS. These are just the homomorphisms from pi1 of the surface, the first fundamental group, to G. Right? We consider that, then the character variety, quote unquote, is just the quotient of this log GS by G. Now, let's see an example. So if our surface is just a cylinder, or if you wish a punctured disk, like over here, then, well, pi1 is just Z, so it has a single generator. And to define a homomorphism, we just need to tell where this generator goes under our homomorphism, right? So there will be G worth of homomorphisms. And as we mod out by G, so G acts by change of, G acts by conjugation here. And clearly G mod G is not a variety, right? Because G doesn't act freely. So that's a problem. So this log GS is really not a variety. It's a stack instead. All right. So we can fix it in two possible ways. First of all, instead of considering geometric quotient, we can consider a GIT quotient, right? So we can instead just take a log GS mod G, which is just by definition, we take regular functions on our on the space of homomorphisms and take G invariant functions and then take spec of this affine variety. Okay, so that's one thing, and people do use it, right? Another way to deal with this problem is to actually consider trivialization, right? So we trivialize our local system somewhere. Now, what does it mean to consider trivialization? This is just adding another factor of G, right? So we have G worth of trivializations, right? And then we have G worth of homomorphisms, right, from pi1 to our group G. And now as we mod out by G, right, so the way our gauge group acts, so this is the element of the gauge group H, right, so it acts by right multiplication on the trivialization, and then by conjugation on the monodromy. Well, all right, so since it's acts by right multiplication, we can just mod out by this section and just get a group G. Then various people worked on this topic, hundreds at least, and there were constructions first due to Atiyah-Bott and then Goldman and finally Falk and Rossley, which explain how to put Poisson structure on this character variety. So this log GS really becomes a Poisson variety, and as such, it admits a quantization. And there were different approaches to this quantization. So let's maybe briefly remind what they are. So the first one is via ARM HSS, and these are due to Falk Rossley, the classical description, and due to Alexeyev, Gross, and Chalmers, the quantum description. So what is this thing about? Well, you can really look at you can really replace your surface with a fat graph and just look at connections on the fat graph or local systems on the fat graph. And you can then try to write some Poisson relations between matrix coefficients or traces of these kind of monodromes. And what Fock and Rossley showed is that these relations are given by some classical R matrices. And what was done in Alexei versus Schomer's, this picture was quantized, so you can present these algebras as some kind of RTT type relations. So some relations satisfying some algebra satisfying R matrix relations. Another approach was in terms of skein algebras, and I'm sure that this list of references is incomplete, but well, the ones that I keep in mind always is Berezitsky and Turev. And in a very simple-minded way, you can just say that, well, this is like looking at what this approach has to say if instead of looking at matrix coefficients of monodromes, you look at traces of the monodromes. And then you'll see that these traces of the monodromes satisfy some beautiful skein relations, which are very geometric, topological rather. You can draw them and write, can express these relations by drawing pictures. Now, a whole new twist to the story came when there was, from works of Fock, Goncharov, and Goncharov-Shen, and these were via cluster algebra. So I'll talk in details about, well, not in detail, but I'll just explain what gets into this approach. And finally, the last, at least historically, the last one so far was via factorization homology, and that was done by Ben-Zvi, Brochet, and Jordan, based on earlier work of Ayala, Francis, and Tanaka. Now, the goal of this talk is really to relate the third and the fourth one. I'll discuss them. Now, I come from people who study cluster algebras, and my involvement in this project was my attempt to understand what factorization homology has to say about it, or at least what factorization homology is, at which I failed. But I'll try to share, the little bits that I've learned. And on the opposite side, if you kind of like categories and you like representation theory, but don't like cluster algebra, I might at least kind of show you some instance of how cluster algebras naturally appear in this language of categories and representation theory. All right, so before I proceed, let me make one remark, is that kind of these first three approaches, what they really work with, they take the global algebra of functions, the algebra of G-invariant functions on our local systems, and quantize that algebra, right? So in a sense, oh, sorry. Actually, can I do that? Yeah. Brilliant. Okay, perfect. Sorry. Right. So in a sense, they only kind of see the fine variety. Whereas if you work with factorization homology, this approach is designed in such a way that it sees the whole stack. So it sees a geometric quotient, right? And the way it does it, instead of working with G-invariant functions, it rather works with G equivariant quasi-coherent sheaves on this space of homomorphisms from pi1 to G. All right, now let me just show you some ingredients that come into this kind of cluster world. Right, so remember how in order to actually make it an affine variety, we introduced G-trivialization 2 slides ago. And what Fock and Goncharov suggested is, okay, let's not introduce G-trivializations, but rather let's introduce some G mod B or G mod B, well, in a sense, trivializations, but to say it more precisely, that's what they did. They said, okay, first let's consider surface with marked points, right? So we'll have a surface with some marked points on the boundary and with punctures, which for me just, if a boundary component of the surface does not have marked point, I kind of shrink it to a puncture because I only care about topology, and I call it a puncture. And then at each marked point or a puncture, I can introduce a section of an associated G mod B or G mod N bundle, right? So let's look at a couple of examples. Well, for example, I just can consider a disk with 3 marked points on the boundary. Now pi1 is trivial, so I don't have any local system. But now I have marked points, 3 of those. So at each marked point, I have a flag, a G mod N flag, and my character variety or moduli space of local systems would be just 3 copies of G mod N mod G, right? And if I have kind of bigone with just 2 mark points, that's same thing as G mod n square mod, G mod n square mod G. Now, in order to have a variety, I always require that all the flags and all the monodromes, they're in generic position. And indeed, if I have 2 flags in generic position, one in G mod n, so framed flag, and one in G mod b, then it's a G torsor, so I can indeed mod out page. Right. Now, and the next idea was to actually choose, well, take a surface, choose a triangulation of the surface, which they call ideal triangulation. It's a triangulation whose vertices are precisely marked points and punctures, and then kind of glue the surface together from triangles and consecutively glue this character variety from those, from triangles. Right? So that's the idea. Now, what does it come with? So if you do that, then you have the following interesting properties. So first of all, each triangulation gives rise to a chart on your variety. And moreover, these charts have, so they are called cluster charts, and they come with log canonical coordinates, right? So each chart will be isomorphic to C star to some power to the dimension of your variety, and we have log canonical coordinates. Now, when I say log canonical, I just mean that if you take 2 coordinates, let's say x, x, j, and xk, their Poisson bracket is epsilon j, epsilon jk, xj, xk, right? Now they're called log canonical for a reason, because if you take logs of those, they just become constant coordinates. So maybe they should have been called log constant. And well, they're not their bool coordinates. They're kind of exponents of their bool coordinates. Well, ideal, of course, we'd like to have, well, just I'd like to have this like very, very boring, and I just have global bool coordinates. So this we cannot have, but we can have kind of chart in which we have, in each chart we have this global exponents of their bool coordinates, and then we have some very nice combinatorial gluings between the charts. Right? So that's kind of the game here. If you have that, then you automatically have a canonical quantization of the algebra of functions by simply quantizing all the charts and then quantizing the gluing data. So the way you quantize charts, so if your chart was C star to some power, then with log canonical brackets, then you quantize it to a quantum torus. So it's an algebra with dimension many generators and their inverses, and all the generators Q commute. This Q, so AB equals Q to this epsilon, sorry, xj xk equals Q to epsilon jk, kxj, and this precisely quantizes this Poisson bracket. If you can verify it if you take quasi-classical level. Moreover, this quantization actually comes with a canonical Hilbert space representation. And let me just say one word about how this representation is constructed. So if you have a quantum torus, you can construct a homomorphism from this quantum torus to a Heisenberg algebra, or rather to completion of the Heisenberg algebra, because what you'll be doing, you'll be sending, say if you have 2 generators which Q commute, you can send one to e to the x and another to e b d over dx, where b is this parameter of the quantization. And then you know that then you can consider representations of Heisenberg algebra, which is up to unit equivalence unique because it's done by Neumann theorem. And you can pull back, and that's how you consider representation of a single chart, and then you introduce some gluing data between the charts, which provides you with the unitary equivalences between these representations. So what happened is I made a bunch of choices along the way, right? To write the representation of this algebra, I first chose a chart. I've chosen a chart, and then I've chosen some polarization of the chart. So some half of it acts by multiplication, half by shift. But then when I pulled back, I realized that, well, up to unitary equivalence, nothing mattered. My choices didn't matter. So that's how I construct this representation. Unfortunately, and it's a really important point here, I don't have a better, well, I mean, okay, forget me, but like no one has a better definition of these representations, and that's sad. And I'll explain why. Moreover, this construction actually comes, it's this gamma S equivariant where gamma S is a mapping class group of the surface. So not only that you have representation of this algebra, but you also have an action of the mapping class group on the algebra and on the representation. And if you forget the algebra now and just leave the mapping class group, then you have a mapping class group representation. And these representations are labeled by by parameters lambda, which classically tells you the eigenvalue of the monodromy around punctures. Now, and there's a conjecture which is called modular functor conjecture. It's a conjecture in what people call higher Type Noether theory, that this representation can respect cutting and gluing of surfaces. So what you're aiming at here is the modular functor, which is literally a collection of representations of mapping class groups on surfaces. So for each surface, you get a representation of the mapping class group, and then this assignment respects cutting, gluing, and this is if the life is very nice and easy, and then this is the same as having a 3D TQFT, and it's the same as having a modular tensor category. Unfortunately, since these representations are infinite dimensional, they're Hilbert spaces or even some Schwartz subspaces of Hilbert spaces. You don't have that. It's not as nice, but at least you can hope that there's some sort of modular functor. All right, so that's the cluster side of the story. Now, note two things about it. So first of all, if we want to work with algebras, we really cannot consider the simplest possible surface that we would like to consider. We cannot consider just a disk, right? Because what's a disk? Well, what's local systems on a disk? It's just a point, right? Because pi1 is empty. But then you have the kind of G symmetry. So really, as a stack, it's point mod G. Right, so point mod G, of course, doesn't make sense as it's non-affine variety. It doesn't make sense as you can consider algebra functions on it. But from the point of view of quasi-coherent sheaves, that makes perfect sense, right? Because what you're considering a G equivariant. You consider G equivariant quasi-coherent sheaves on a point. So quasi-coherent sheaves on a point is a vector spaces. G equivariant, you're just considering G representations. So this is rep G, right? Ideal, right? So then this will be our starting point. And another thing which is really mild, but if you work with cluster algebra, you might have seen this problem, is that, well, if you have a puncture over here, let me zoom in. You have a puncture, then at the puncture you have this section of the G mod B or G mod N bundle, and you have a monodromy around this puncture. And if you seriously want to have a section of this bundle, then the monodromy has to preserve that flag, whether this flag is in G mod N or in G mod B. So you have two choices. Either your flag is in G mod B, or you have a framed flag, it's in G mod N, but then your monodromy has to be unipotent, because otherwise it wouldn't preserve G mod N. In some cases, you would actually want to consider kind of G mod N flag at the puncture, and you cannot, because that's just not part of the story, and we'll discuss how you can actually make sense of it. All right. Now, so I'm done with cluster algebra bit. I would like to consider it with something that factorization homology tells us. So what does it say? And what is this construction at all? So first of all, let's just fix our reductive group G once and for all. And then factorization homology in the first approximation is kind of this assignment. So to each surface, I want to assign a category, right? So S will be surface, ZQ of S will be category. And then I really want some functoriality property from it. So what I really want, I want the ZQ to be a monoidal functor. So which means that I'll tell you how I'll explain that this is part of some category. This is also part of some category, or an object in the category. And I have monoidal structure, and I have monoidal functor. Moreover, I want this ZQ to somehow know about action of the mapping class group. So which really means that instead of categories, I have to consider two categories and consider natural transformations. And then I want it to be local in S in the strongest possible sense. So it's not a mathematical term here. It's just saying that I really want to make sense of the simplest pictures possible, right? So that's what factorization homology will have without even describing what it is. And if we have all that, then clearly we have gamma S equivariance because it's part of the construction built in. And second, we obviously have modular function because, again, it's built in, right? So then if we have this God-given setup, well, fantastic, we're done, right? So now if you work with cluster algebras, you kind of define everything very nice in terms of generators, relations, coordinates, and so on. And then you need to prove that you have a modular functor here. You define everything through abstract nonsense, but then you really have to calculate something, and if you define something with abstract nonsense, it's really hard to calculate, at least for me. So the only thing I learned more or less from this story is that, well, A is not as abstract and B is not as nonsensical, and I like to try to share this. Right. And another comment here is that really from cluster algebra approach, what we see, right, well, to each surface, we kind of attach an algebra and the canonical representation, whereas in this approach, to each surface, we assign a category, right? So somehow, really, it's this interplay between kind of constructing a 3D T50 and the 4D T50. And that's, so this story is kind of, it's about some special 4D T50, whether cluster algebra part is about Chern-Simons in different guys as well, to be precise, SLNR Chern-Simons. Right. Now, again, I haven't defined factorization homology, but I'd like to make some statements about it, and then I'll explain what it is. So there was this work of Ben-Zvi, Francis, and Nadler, which explained the following. So let's say that the Z, so now I'm talking about some classical picture. So this Z of S is a surface as it used to be, and Z of S is this factorization homology, which I will also denote as kind of integral over S of some category. And this category will be called, so this is called factorization homology with coefficients in this category, in rep G, right? They constructed this thing, and then they proved that really this category that they assigned to a surface is really just the G covariant quasi-coherent sheaves on this homomorphisms from pi1 to pi1 of S to G, right? Or equivalently quasi-coherent sheaves on the moduli space of local systems. G-local systems on S. And then there came work of Ben-Zvi, David Ben-Zvi, Adrian Brochet, and David Jordan, which kind of quantized the story. And what they did, they really just replaced this rep G with rep QG, which are integrable UQG modules. And then they explained how this category relates to a work of Alexeyev, Gross, and Chalmers. And I'll just tell one thing, that somehow, if you had an affine variety to start with, so if you considered local systems with framing, then your category will actually be isomorphic to a category of modules over some algebra. Somehow being isomorphic to, being equivalent to a category of modules over an algebra is the same as being, category of quasi-coherent sheaves on a quotient is only equivalent to a category of modules over some algebra if the action of the group was free, right? And in that case, this algebra which you take the modules is isomorphic to this, let's say, Gross-Chalmers algebra. So direct quantization of Fock-Rosse structure. All right. And now I want to formulate the theorem that we proved and spend the rest of the talk explaining what's actually said on this slide. So first of all, instead of surfaces, I'll consider stratified surfaces, and I'll explain what it is. Now, what I will consider then is this kind of factorization homology with coefficients in this weird guy here, which is somehow, so this will involve not just rep QG and rep QT, but also rep QB, right? So I have G, I have Borel, B, I have maximal torus T, and I'll consider these categories of some modules or UQG, UQB, and UQT. Now, S is simple, and again, I'll explain what it is. More or less can be glued from triangles. And G is of rank 1, so this part. And as usual, rank 1 condition is not something that important. It's just that combinatorics becomes harder in higher ranks. And that's why we kind of were lazy enough to do it for high ranks. Then each triangulation of our surface will kind of give us a chart. Now, what's a chart in this categorical setup? So chart is just some subcategory, so some open subcategory, which is actually isomorphic to modules over some quantum torus. Right? And the way you should think about it is, action of G on our variety is not free, but I can consider some open chart on our variety on which the action is free. And I hook up a category of modules over this quotient of the chart mod G. So that's that thing here. Right? And moreover, well, if you have two charts, I kind of have a transition functor between the charts, and this transition functor is given by cluster mutations, and that's not really that much of a statement. It's really just kind of story about so for Conjecture, they first did everything classical, and they said, well, we can just quantize cluster algebra purely in cluster algebraic settings. And here we're recovering their construction, but from geometry. Sorry, from representation theory. All right, and now I'll try to explain what is said on this slide. So first of all, what are stratified surfaces? And actually, let me check how I'm doing. Right, what are stratified surfaces? A stratified surface S is our old oriented surface along with the following data. So first of all, I want to have kind of one-dimensional walls inside the surface, and the wall will be just it's an embedded circle inside the surface, or an embedded segment, so that the boundaries of the segment are on the boundary of the surface, like over here. So this is a wall, and this is a wall. Then walls subdivide my surface into two-dimensional regions, and I want to color each of the regions either by G, so the group, or T, the maximal torus. And in all my pictures, I'll draw purple. I'll color G regions with purple and T regions with yellow. And I promise I won't write anything in T regions except for letter T. So hopefully it will not obscure, the yellow color will not obscure anything. And then the third ingredient is I consider a collection of what we call gates. And these are, we mostly put them on the boundary, but in some examples that I'll show you on the next slide, they will be not on the boundary. So let me actually erase this. So gates, you can see them here, here, and here. And somehow the reason we call them gates is somehow we were thinking of, well, you can kind of open this gate here and insert a T-disk inside the surface, right? But really what this means is we will consider a trivialization or framing of our local system at this regions here, right? So here we'll have a G, sorry, G framing, here we'll have T framing. All right. Now we have stratified surfaces, then, well, I promised to talk about character varieties. So we'll also have stratified local systems and moduli spaces of those. So what's a stratified local system? Well, okay, it's a G-local system. It's a triple. It's a, well, actually quadruple. It's a G-local system on the union of G regions. It's a T-local system on the union of T regions. It's a B reduction of the G cross T local system along each of the walls. Now, what's a B reduction? It's a B sub bundle inside of G cross T bundle, right? Now, how do you form a B sub bundle inside of G cross T bundle? Well, you have two natural maps. You have an embedding of B in G because B is a Borel inside G. And then you have a quotient map from B to T, because you can think of this maximal torus as just B modded out by the commutator, right? So you have two canonical maps from B to G and from B to T, and then you can take diagonal map inside the B inside B cross B, and then map it to G cross T. And with respect to that map, I can consider B sub bundle inside of G cross T local system. So that's the B reduction. And finally, as I said, we'll consider framing or trivialization set at this gate. Now, this gadget here, so it's kind of character variety defined from group G and stratified surfaces with framing. So this will be just this moduli space of stratified local systems with trivializations at all the gates. And if I don't write framing, then I just mod out by the action of G and T at every single gate. So if I write G with subscript S, that just means that it's a collection of all the G gates in my surface. And what are examples? Let's see examples, and let's see examples of this stratified local system. So if I consider that disk over here, right, with two trivializations, well, this piece alone give me G, right? Gives me G. This piece gives me T. So now I have just G cross T. I need to mod it out by B. So it's G cross T mod B. But just because of how I define this action of B, right? This is the same as G mod N. Okay, at least we know we can recover G mod N. Like, fantastic. If we delete this trivialization, it's additional mod N covered by T. So we recover G mod B. If we delete this trivialization, it's G mod N mod G, so it's point mod N, and here it's point mod B. Right? So here are our basic disks. Let's consider more examples. I'm really fond of this picture. I'd like to convince you that this type of mod-like spaces, they appear a lot in geometric representation theory. So let's consider this surface, right? So what is it? So first of all, over here, well, here is a G trivialization, right? Which will be killed when we mod out by G. Now we have a G local system, right? So that's that guy here. And we have a B reduction in G cross T, so just a flag in G, and we don't have trivialization here, so just a flag in G mod B, which, because of how this picture works, the flag has to be preserved by G, right? So that's precisely pairs G and F such that G preserves the flag. So this is the total space of the multiplicative Springer resolution. Now, you can play the same game, but you consider different surfaces. You consider disk, where this whole region is T region, and we'll also trivialize at some point. So it will be the same story, except for now the T local system will have to be trivial. So we now have G and a flag in G mod N, because we now have a trivialization, and G will have to preserve F, so G will have to be unipotent. If we kill this trivialization, it will be paired G and G mod B, where G is unipotent. And finally, if we consider this surface with two trivializations, right? So what is it, right? It's a G local system here, T local system here, a flag in G mod N, but then there's a condition on how G local system or how G monodromy or T monodromy act on the flag. And the condition is really that G acts on F the same way as T inverse acts on F, right? And of course, if it's that way, then you can just forget about T completely because you can restore it from the action of G, right? So it just means that G scales the flag, and it's the same as G in your group framed flag, so that G only preserves the G mod B part of the flag. Right? All right. And finally, to convince you that it's even more interesting than I showed so far, if you glue two of such pictures together along just this line, so you get something like this. This is just by the same reasoning. It's the multiplicative Steinberg variety. Right? So, and that's something that, well, at least I know and like, and I hope you guys also know and like. All right. Now, what's stratified characterization homology? So this is all done. This is all work of Ayala, Francis, and Tanaka, and well, I promised that it's some functor from some category of surfaces to some category of categories. Right? So category of surfaces, it will be a two category. It will be monoidal and symmetric, and the objects are stratified surfaces. One morphisms are stratified embeddings. So it's embeddings of stratified surfaces which preserve all the data, which preserve the walls. G regions have to go to G regions, T have to go to T regions, and two morphisms are isotopics. Now, monoidal structure is just given by disjoint union. So that's some very simple structure on surfaces. Now, inside that category, I can consider a full subcategory. So it's a full subcategory generated by these surfaces, right? So this is a disk fully colored by G. Let me actually put it here. So this is a G, this is a G and T, and this is T. So this is a G disk, I'll call it DG. This is a T disk, I call it DT. And this is a B disk, which is the name for a picture with one wall, G region and T region. And then I consider these objects, and I can take their tensor products, so the joint unions, and I take the full subcategory of this thing. And then stratified vectorization homology is literally the following universal construction. So first of all, I need to fix some symmetric monoidal functor from this disk category to that gadget here. So, so this gadget here will be, so it has a name, but the gist of it is that objects are two categories. And well, one morphism and two morphisms are sorry, universal natural transformations, right? So and if I have right now I have an embedding of the disk category inside surfaces, and if I have such a functor from disk to this presentable to categories, then by some abstract nonsense, at least to me, which people call Kahn extension, or left Kahn extension, you have a unique functor, which is called stratified factorization homology. Right? So as long as I specify what happens to the disks, some universal construction tells me how to assign a category. Although obviously this definition, if that was the only thing we knew, that would be quite useless because we cannot calculate anything with it. But luckily you can. Now let's discuss what kind of structures should be assigned to the ZQ of these guys. Well, first of all, our function applied to this G disk. Well, first of all, we can take two disks, embed it into one bigger G disk, right? So it has to be monoidal, and then also we can take we can rotate these disks, 180 degrees. So it has to be braided monoidal category. Okay. Same thing goes for the T disks. It also has to be braided monoidal category. Now, what about B disks? Well, if we take two B disks over here, obviously we cannot now rotate them around one another. So it's not braided, but it's still monoidal because we can include two B disks into a B disk, so it's monoidal. But moreover, it receives a monoidal functor from the standard product of categories of this category and that category, right? Because if you have for example, a G disk over here and a B disk over here, then you can include it into one B disk, right? Okay. And moreover, as you can see, you can somehow braid a B disk with a G disk by doing the following. You can take B disk and include G disk into another B disk like this, or you can take a B disk and include a G disk to be like this. And this is what people call half braiding, and I'll show in a formula what this really means. Right? So now what we want to do, we want to find some categories that will have all these properties, and these categories will come from representation theory of quantum groups. So for this category, I'll take RepQG, so it's integrable UQG modules with braiding given by R matrix. For this category, I'll take RepQT, so it's UQT modules, and UQT is a commutative algebra, but I can still have a non-trivial braiding. So what are objects in this guy in this category, right? So they're just vector spaces spanned by weight vectors. And now the way I define braiding, if I take two vectors v lambda and v mu with weights lambda and mu, that's the way braiding works. It's q to the pairing of lambda and mu, v mu tensor v lambda. And for that guy, I'll take RepQB, right? So it's integrable UQB modules. Now, since I had maps from B to G and T, I have maps backward from RepQG and RepQT to RepQB. And the half braiding works literally like that. If I take V in RepQG or RepQT, it's your call. I will say it's in RepQG. I first map V to a UQB module, tensor it with another UQB module. And then I want to map it to, I want to swap them. I want to have a morphism to M tensor I star of B, right? And well, I first apply R matrix, which acts on here indeed, and then I apply permutation, right? So that will give me this half braiding as in my picture. And indeed, if you see what happens here, it's just a map from G to B, and then I do some sort of braiding. All right. Now, factorization homology is by construction functorial, right? So if I have embeddings of surfaces, sorry, it should be stratified surfaces. Then I have this functor here, and it's also again more or less by construction satisfies excision. If you wish, you can think of this factorization homology as some construction that you asked to assign categories to surfaces in such a way that your construction satisfies excision, and then you try to solve this problem, and you find that this solution actually exists, but is rather abstract. So the excision is the following. So if you take your surface S and you cut it into two surfaces S1 and S2 that cross over some color over here, so it's a cylinder, then first of all, these two categories assigned to the left piece and the right piece of your surface, they are module categories for category over that cylinder, right? So you can have a functor from ZQC tensor ZQS1 to ZQS1, and same for 2. Also, to this thing by just stacking cylinders, you see that you should assign a monoidal category. And finally, the excision, the excision property is just saying that ZQS is a kind of tensor product of ZQS1, ZQS2 over ZQC. An example of such a construction is, imagine now that I take what I call a 2-disk. So it's D2. It's one G region and two kind of boundary T regions. And I can glue it from two B disks along a G disk, right? So that's what's going on here. But now, in order to kind of proceed, I really need to understand sort of how I can think of this B disk as a module for this G disk. And that's one of the kind of maybe most important things here. So let's think of it classically first. So instead of rep QB, let's consider just rep B, right? It's B modules. Now, if you have B modules, you can always send them to this thing. Well, first of all, what's B modules? As we discussed, it's quasi-coherent sheaves on point mod B, right? Because quasi-coherent sheaves on a point, it's vector spaces, point mod B, it's B equivalent vector spaces, so B modules. But I can as well write it as G as quasi-coherent sheaves on G mod B on the flag variety mod G, right? Or equivalently, I can think of it as G equivalent quasi-coherent sheaves on G mod B. But I can as well think of it as G mod N equivalent quasi-coherent sheaves, G cross T equivalent quasi-coherent sheaves on G mod N, because I can further mod out, write this G mod B as G mod N additional mod T. Now, why I'm doing that? Well, because I want to get to affine varieties as close as possible, and G mod N is not affine, but at least it's better than G mod B, which was projected. Right? So G mod N is quasi-affine. And of course, I would like now to say, well, if G mod N were affine, if G mod N, let's look at this example when G is SL2, so G mod N is not C2, but it's almost. And I would like to say, oh, well, this category is just G cross T equivariant of C2 modules. But it's not true because G mod N is not C2, it's C2 without the origin. So instead, what I have an embedding of this category inside this quasi-coherent sheaves on C2 without equivariant quasi-coherent sheaves on C2 without origin. And really, you can identify it with kind of right orthogonal in quasi-coherent sheaves on C2 to sheaves supported at 0. So you take sheaves supported at 0 and you take an orthogonal complement in the sense that if you home from sheaves supported at 0 to your objects that you think these homes should always be 0. And now you can quantize this. So what will be a Q version of that story? Well, the Q version is instead of G mod N, you consider, or instead of functions in G mod N, O of G mod N, you consider quantized version of that. So you consider OQ of G mod N. And this is indeed an algebra object in rep Q G cross T. So you have a G action, you have a UPG action, UPT action on that. And also let's just remember that what's OQ of G mod N, right? It's if you wish, it's well, OQ of G is matrix coefficients of UQG. And when you say OQ of G mod N, that's matrix coefficients. So what's the matrix coefficients? You take a vector and covector and you pair the two, right? Now, if you mod out by n, it means that one of those vectors or covectors have to be highest weight or lowest weight depending on how you chose your n, right? So this is kind of pairing of any to say highest, right? And you can really write it as by Peter-Weyl theorem, you can write it as kind of sum of all dominant weights of G module with highest weight lambda, tensor T module with highest weight minus lambda, or sorry, lowest weight minus lambda, but lowest weight minus lambda. Now, inside this OQG mod N modules, sorry, G cross T equivariant OQG mod N modules, you have a subcategory of torsion modules. So what's torsion module? Well, modulus torsion, if for any element, for any vector in this module, there exists some weight which is high enough, that anything higher will actually kill this module, will kill this vector, right? So these are torsion modules. And one theorem that we managed to prove with David, Ian, and Gus is that this rep QB can be identified with right orthogonal to torsion modules inside OQG mod N modules, inside G cross T equivariant or UQG cross UQT equivariant. OQG mod N modules, right? And again, this kind of this guy here, right? It's objects are such modules in here that for any torsion module, the home is 0. All right. Now, as we have that, we can actually compute, well, at least attempt to compute this category. And the way we're going to compute it is the following. So remember that, so first of all, remember what I just said on the previous slide, that this algebra is really just the direct sum of all dominant weights of V lambda tensor chi minus lambda, right? This is the highest weight UQG module. This is a lowest weight UQT module. And by Schur's lemma, if you have tensor product of two such guys and you take UQG invariant, right? This is actually, well, kind of, your invariant is your algebra of invariance is a commutative algebra, which is labeled by just dominant weights. And this statement is really the same as saying that if you have two framed flags in generic position, in G mod n, and another, say G mod n plus and G mod n minus, G acts freely, and when you mod out these flags in generic position, G mod n plus cross G mod n minus mod G, you just have a torus. So that's really quantum version of the statement. And this guy here, well, it's some sort of a calculation. So here I'm not just taking tensor product, I'm taking braided tensor product, which means that as vector space, nothing changes. So this doesn't change the statement that I just made, but it will be important for the next statement. So what I'm doing, I'm considering this algebra, which at each factor kind of behaves within itself as just OQG mod n. But if you want to commute the two factors, then you need to use some R matrix relations to commute kind of something from the first factor to something from the second factor. And then, as I said, it's a kind of calculation that tells us that like before, when we're embedding our category that we assigned to a B disk inside OQG mod n modules, here we'll be embedding category that we assigned to this disk with one G region and two T regions, so this D2, inside modules over this braided tensor product. And you have to take UQG cross T squared equivariant modules. Now, because you have two T regions and trivialization at each of them. All right. And now I would like to somehow still, so that still doesn't tell me much about this category over here, because, okay, I know where I can embed it, but I'd like something, I'd like a category inside of it, I'd like a chart. So how do I do it? What you can also show, and what we did show, is the following. So you can take this category of this braided tensor square modules, G cross T square equivariant, and then you can take only those modules on which your UQG invariant elements act invertibly. So this is how I denote it. And now, if you inverted those elements, then the function of taking UQG invariance is conservative, which again, well, I'm as confused about word conservative as probably more confused than anyone else in this room. But for me, it's just a statement that somehow it's an analog of saying that if you have two copies of G mod n, which are in generic position, then G acts freely. So that's somehow when I invert, if you use principal minors, it guarantees that these two copies of G mod n are in generic position, G acts freely, so I can just mod out by G. And when I do that, what I recover is this quantum torus algebra, on which I have two T actions, residual actions from this G cross T square action, because I modded out by the G action, I still have the T square action. So this is just a quantum torus. So in other words, what I got is I got a subcategory inside of here of T square equivariant modules for some quantum torus. And really, if I'm seriously in SL2, then this is just a commutative algebra generated by element delta and element delta inverse. Okay. Now I can play the same game and see what happens in a triangle, right? Well, kind of very similar things happen. And indeed, inside of this category that we assigned to a triangle, I'll find an open subcategory of modules over a quantum torus. Now, T-cubic variant, where this quantum torus is generated by these three elements and their inverses, kind of corresponding to kind of these three sides of the triangle. And the Q-commutation relations are like they just Q-commute. Right? So this now you can see that we're recovering cluster charts. Now, if I go further, if I look at the squared, so it's now a disk with 4 T regions, I can cut it into triangulations in 2 different ways. I can cut it like this, and I can cut it like that. Right? Which means that I'll have 2 open subcategories, this one and that one. And well, now what is the situation that I have? So this is really modules over localization of some algebra. This is modules over localization of the same algebra. And now I can consider a category where I can combine the 2 localizations. So here I inverted inverted the G equivariant element corresponding to one diagonal. Here I inverted G equivariant element corresponding to the other diagonal. Now I can, if I want, I can invert both, and it will be an algebra that contains both of these localizations. And then, indeed, I have a functor from one to another where I just take a module over here and send it to this module tensored the biggest localization, tensored over, well, that algebra, which gives me a residual action of this algebra. And the last thing to check is really how these elements commute with each other. And you can indeed, it's a simple calculation. You can check that the Q commute. So this is a skein relation, or this is a relation between quantum cluster A variables, or people also call them quantum cluster K2 variables. So in this way, you recover the quantum cluster relations, but somehow not from just abstract quantization cluster algebra, but from some representation theory that you've seen. All right, so let me try to summarize what I said. So we kind of build this bridge between cluster algebraic approach to quantizing character varieties and factorization homology. Right? So factorization homology at least allows us to not just quantize algebras, but to quantize and like affine varieties, but to quantize stacks. Okay, this construction is a priori functorial, which is good. Cluster algebra brings some means of calculating something in terms of these factorization homology constructions, because you can, well, you cannot really tell what the category is, right? But you can test it against some open subcategories that you know everything about. They're just modules over corresponding quantum toric or quantum cluster charts. You can now treat indeed this case of framed flags sitting at punctures. You can actually do slightly, if you don't like all this categorical stuff and you like generators and relations, you know how, well, cluster structure is rather rigid. So you have, I mean, sorry, maybe rigid is not the word, but it has, well, it has a definition. And if you're an SL2 case, and you indeed look at the triangle, at the moduli space of geolocal systems, at the disk with 3 marked points, on which regions as here, you have just single cluster chart, and there's nothing else you could do. That's it. Now, in this case, what we can do, we can open as many T gates over here and as many G gates over here as we want, which will actually give us a different algebra. So as long as we have at least one, so having one gate or having million gates is not visible from the point of view of the category, because taking the corresponding invariant, so if I have, say, 2 T gates over here, and I decide to close one, so I decide to take T invariants, this function will be conservative, so I'll have an equivalence of categories. But the algebras a priori will be different, and we actually use this algebras with more gates to show how to and explain how things are glued over here. In particular, it means that you have kind of more elaborate cluster charts, which indeed help in all the calculations. So, for example, this there's a rather standard problem in constructions when you somehow define something from triangulation for one triangle, for each triangulation. Then you have to check that what you defined matches across triangulations. And then you need to find a path from one triangulation to another, check that as you go through this path, your construction kind of works well, and check that the result doesn't depend on the path you've chosen in triangulations. And in dimension 2, you have self-folded triangles. So you have triangles where you identify this side and that side. So it just becomes kind of this disk with a puncture. And it's still fine, you can still work with it. But in dimension 3, you have worse effects. When you have tetrahedra and you glue them together, and you have self-folded tetrahedra, and there it actually becomes a serious problem. But if you're willing to open kind of 1,000 more gates, you can always treat all these constructions in the same spirit. So in a sense, this gives more freedom. It gives more freedom from the algebras you work with, and this is useful even for people who are like generation relations oriented. And finally, I want to. It's probably bad taste, but I want to end this talk with some sort of complaint that I was kind of hoping to see how this universal construction helps me say something about this modular functor in higher Muller theory, right? And well, because this construction just tells you, well, if you kind of can apply this factorization homology magic machinery to the category, well, you just get the modular functor right away. You don't need to do anything. But of course, you cannot apply it to these representations that people in classical algebra study just because there is no definition of a category. And that's what I started from, right? So one problem that I'd like to advertise, if anyone is interested, is that I really would like to have a definition of these kind of Hilbert space representations of quantum cluster algebras and of quantum groups that people call positive representation, that was studied by Poisson and Teschner and Frankel and Eve and many other people. Because so far, these representations are a little like principal series, but not quite, because they're closed under tensor products. But the only definition we have so far is in terms of generation relations, which is completely inadequate, and I really like a better one. Right. Thank you.
Are there some questions?
Thank you for a nice talk. I have two questions essentially on the literature. So your decorated surfaces.
Mm-hmm.
So, right, there was the story of decorations by Leblanc and Severa.
Mm-hmm.
So how your decorations, how are they related to those decorations? Is it the same, or is it like different, or?
To be honest, to my shame, I completely forget what they had. I'm sorry.
Okay, check.
I know about their work, but I just completely forget.
Then maybe, sorry, another question on the literature. So with this SL2 stuff, he has all those skein relations also with decorations on the boundary. So, but then for that, you probably know the answer, how this stuff is related.
Right. So let me give a answer to marginal different questions. So there are all kind of flavors in which these quantizations come, right? So and then of course, the natural question is how all these four approaches are related. In particular, as I said, there's this work of Ben-Zvi, Rocher, and Jordan, where they, without additional decorations, just where everything is colored by G, they related to quantization by U and co-authors. There is another work by Juliet Cook, a graduate student of David Jordan, relating it to skein algebras. On the cluster side, there is a a folklore really relating, folklore that part of which was written in a recent paper by Michael Shapiro and Leonid Chekhov on relating, again, the cluster algebras, cluster quantization with RLL type quantization. There is kind of some work, well, as my friend puts it, work in progress, which hasn't seen any progress in the last few years, relating clusters to skeins. I will be happy to discuss it. As for relating in these factorization homology or cluster, well, really factorization homology with decorations on stratified surfaces to work of less, so that hasn't been done because this is literally kind of the, okay, not the only work, but kind of only work in kind of which might be related to this last work. But you can kind of go through cluster algebra, so you know that these guys are related. You now know how they're related to quantum cluster algebras, and then you can I can explain my ideas how to relate
expect them to be the same or roughly the same.
Yes, I do expect them to be roughly the same. Although what you can easily prove, almost always, so you can prove that RLL algebras are embedded into quantum cluster algebras, and you can probably prove that skein algebras are embedded. So what would be really hard is to show that the homomorphism is onto. And the reason it's hard because the quantization of functions on cluster variety is defined implicitly. You have infinitely many charts. You just say, well, it's functions that are regular in every single chart. And so you don't have any control over generators. You have it classically because you have some codimension 2 arguments. In quantum level, unfortunately, you don't. And even like I don't know how to run any flatness of the quantization type arguments. So that's a problem. In some examples, you would know generators, but even this very basic question, whether, so we have an embedding of the quantum group, or rather, well, Greenfield double of the quantum group into some quantum cluster variety. And we conjecture that it's an isomorphism, and we're 100% sure. We even checked it by some really pedestrian methods for SL2 and SL3. But I don't know how to prove it. Also provided that actually there is a work by Shen who actually proved it classical. So he showed that G dual, the dual to the Poisson dual to the standard Poisson group is actually isomorphic to the classical functions on to the classical cluster Poisson group. So
okay, thank you.
Yeah.
More questions? So you're saying this cluster method, they sort of provides certain chart for what you are calculating, something more global.
Yeah.
Is it?
Yeah.
Like what is the the result you got is a category of
right. So what we had here is we had some abstract construction of the category that this factorization homology assigns to a surface, and you have this subcategory.
It is a category of algebras.
No, it's definitely not a category. It's definitely not a category of modules over an algebra, because if it were, it would mean that you have a defined variety, and that's not the case. So it's very much not that. It's rather some quantization of category of quasi-coherent sheets. It's a kind of quantum analog of category of quasi-coherent sheets, also equivariant quasi-coherent sheets on your space of Holmes from Pi1 to G. But so it's and this category is rather abstractly defined. But however, you have infinitely many in general open subcategories, each of which does look like category of modules over some algebra, and this algebra is very simple. It's a quantum torus. So it's a bunch of generators which
calculation tool.
Yeah. So in a sense, if you like categories and representation theory, then that's one way to understand what cluster algebra is, or maybe one categorical level higher.
Thank you, and let's thank the speaker again. And
so remember that we have the picture now outside, and after that the lunch, and we'll resume at 3.